Okay, so today we take a look at lesson 3.8. Pause the video and solve the problem of the day. So 3.8 is use inverse matrices to solve linear systems. What we have first is an identity matrix. A matrix with ones on the main diagonal and zeros elsewhere. So for a 2 by 2 identity matrix, here's my ones, here's my zeros. 3 by 3, here's my set of one diagonals, zeros elsewhere. In this lesson, we're only going to focus on 2 by 2s. So what's an inverse? Two n by n matrices whose product is the n by n identity matrix. So to give you a little bit of a heads up, first of all, identity would be like, you don't have to write this down, but 1x is the same as these identity matrices. It's like we want to get this equals 1. Instead of saying 1x, we have to do it in matrix form. Now an inverse, for instance, what if I give you 3x equals 6, right? How would you solve for x? Well, I divide by 3, right? But isn't that the same as saying multiply by a third? And whatever you do to one side, you have to do to the other. So multiplying by a third undoes the 3, right? So if you think about it, we could almost say this 1/3 is an inverse, but we want it in matrix form. So multiplying by like the opposite, that when you multiply these two together, when I take 1/3 times 3, what do I get? I get 1x, or I'll type it over here, 1x equals 2, right? So 2 n by n matrices whose product is the n by n identity matrix. This would be like an identity matrix, just in number form, it's a 1. Now, we have to multiply these. It says in example 1, are the following matrices inverses of each other? All right. So I do this row by this column first. And then what do I get here? I get -8 plus 9, -8 plus 9, -8 plus 9, can I just say it's 1? Okay. Let's try the next one. So I do the same row, and now I'm going to do this column. So you get what? -6 plus -6. -6 minus 6 is what? -12. Now, if I continue on with my matrix here, so I did the first two spots here, the whole row. Do I have to keep going to this row? Hopefully you realize no, because what do we have here? We have a -12, right? What should it be? It should be a 0. So really I could stop there. I know this is not, they're not inverses of each other. Not inverses. All right, let's try the next one. So you have this row and this column. So I get what? 1 times -4, which is -4, plus 5. -4 plus 5 is 1. All right, I'll use a different color here. Let's do the same row with this column. 1 times -5 is -5 plus 5. -5 plus 5, 0. All right. Now we'll move to this row and do this column. -1 times -4 is 4, plus -4, -4 plus 4 is 0. All right. And then last but not least, we'll do this with this. -1 times -5 is 5 minus 4. 5 minus 4 is 1. So yes, in fact, letter B, you see I get the identity matrix when I multiply these together. So these are inverses of each other. So let's write that down, inverses. And that's my answer. Now, we look at multiplying two of them together, right? Well, let's also look in terms of what if I give you a matrix and you have to tell me what the inverse matrix is. So the inverse of a 2 by 2 matrix. The inverse of matrix A, B, C, D is A to the negative 1 stands for inverse. You notice we do 1 over the determinant. This is the determinant, or AD minus CB. Do you see how AD minus CB is here? Now this diagonal will flip-flop places. They'll switch. And then the up diagonal, you'll negate them or make them the opposite. All right, so let's see how we actually, I'm going to actually write this in here. Let's see how we do an inverse. So I'll write down here, it's actually A to the negative 1 is the inverse. So start with 1 over, it's the determinant, what we did in the last lesson. So what do I get here? I get 5 times negative 3, which is negative 15, minus 8 times negative 2, minus 16. So we get negative 15 minus negative 16 or plus 16. Now, to deal with the down diagonal, I think of it as the down diagonal, we switch them here. So this is the 3 now, and 5 go here. And then this diagonal, we change it to the opposite sign. So now negative 2 becomes a positive 2, 8 becomes a negative 8. Now, we simplify this. This becomes what? 1 over 1. So we're almost done. The number in front is now a scalar. Remember scalar multiplication. What is 1 divided by 1? 1 divided by 1, I could simplify just to 1, right? So I'm just going to change it in the step here. This is 1. So I take the 1 and distribute it to all 4 of them, but obviously 1 times itself is just the same thing. So here's my final answer. So this is the inverse matrix. 3, 2, negative 8, 5. All right, pause the video and try the next one. Okay, so I want you to pause the video and solve this, or you should be checking your work. What happens in this one is the determinant is not that nice. It's 1 over 22, right? But it is a scalar just like the one here. So you distribute the 1 over 22 to everything. And these 3 numbers I could simplify, right? 4 and 22 are divisible by 2, so you get 2 11ths. Down here you get negative 1 11th because they're both divisible by 2. And 6 and 22 are divisible by 2. So sometimes they don't always work out nice and neat. Now, you might be wondering, why are we finding the inverse? Well, what if I want to solve algebraically? So let's look at our next example here. Solving matrix equations. Do you see I'm looking for x? If I go back to what I said before, 3x equals 6, right? If I wanted to solve for x, it's almost like a problem like this, but here there's just numbers, 3 and 6, as opposed to matrix. Well, I told you we knew we had to multiply by 1/3, right? Both sides. To undo the 3 here, you could almost think of the 1/3 I want to say as an inverse. These will cancel each other out. You'll get 1x here. Well, that's what we want to do here, but we need to undo this matrix here. And the only way that we could undo it is we could find the inverse, just like we did a second ago. So let's actually just clear this here. So I'm going to find the inverse of this one here. All right, so I'll do it up top. Okay, so I'll do a to the negative 1. So we have to find the inverse of it, so we can multiply both sides with the inverse. So you get 1 over 2 times 4 is 8, minus this diagonal, which is 7. And then this 4 goes here, 2 goes here, 7 goes here, 1 goes here. And if you realize this is really what, 1 over 1? Are you guys okay with me not rewriting it? Because it's a sort of a waste of time, right? If this is 1 over 1 here, 8 minus 7, we would distribute all to that, the 1 to everything. So my identity matrix is 4, 7, 1, 2. Or excuse me, I should say inverse matrix. So what I need to do from here is I'm going to multiply both sides to the left of each part. It matters actually if it's the left or right, but I'm going to multiply them by each side here. So watch. 4, 1, 7, and 2 is here. I'm going to rewrite the original. You write your x. And what I do to the left, I have to do to the right as well. Not writing here, right? All right. If you notice, my inverse is both inverses, one on each side. They're on the left. It's very, very important is on the left. Matrix multiplication is not commutative. So you know how 2 times 3 is 6? Well, 3 times 2 is 6. But that's not the same for matrices. All right, now when I multiply the side on the left here, I'm going to take a quick look at it. What should you get, though? You should really get the identity matrix, right? 4 times 2 is 8. 7 minus 1, or 7 times negative 1, I get 8 minus 7, which is 1. 4 times negative 7 is 28. 7 times 4 is 28. Negative 28 plus 28 is 0. 1 times 2 is 2. So 2 minus 2 is 0. So we're just doing multiplication. 1 times negative 7 is negative 7. Plus 8. Negative 7 plus 8 is 1. So as long as you don't mess up the inverse, your inverse will always be the identity matrix. Now let's take a look at multiplying this way. And I'll write this one out for us. All right, so you do this first with this. So I get what? Negative 84 plus 84, which is just 0. Here's my next group. I move over a column. 4 times 3 is 21. So I say again, 4 times 3 is 12 minus 7 times, so plus 7 times negative 2. So 12 minus 14 is negative 2. And then I do the next one. Do this row, this column. Try not to write over it. 1 times negative 21 is negative 21 plus 24. Negative 21 plus 24 is 3. And then last but not least, let's do this one, this one. 1 times 3 is 3, plus the negative 4. 3 minus 4 is negative 1. So this is my answer. This left-hand side is the identity matrix. So sometimes I just rewrite just as x. So like 1x is x. You're allowed to do that. So here's my answer. My 2 by 2 is 0, negative 2, 3, negative 1. All right, so we just took a look at how we solved algebraically to solve for a matrix, an x. And just as a final note here, if I plugged x back in and we multiplied this by this, you would get this matrix here, just so you know that's what it means. Now let's apply it to a system of linear equations, because we did that in the last lesson with Cramer's rule. So solving a system of equations using a matrix equation. Step 1, write the system as a matrix operation, ax equals b. So I don't actually give you the formula or the equation, you have to write it yourself. It's pretty easy though. Matrix A is the coefficient matrix. Matrix B is the variables matrix. 2, find the inverse of matrix A. Then 3, multiply each side of AX equals B by inverse of A. On the left, once again, it's very important that you multiply to the left, not to the right. Matrix multiplication is not commutative. To find the solution, x equals a to the negative 1b. All right, so this brings us to example 4. I have it already worked out for us, so I could talk about it as we go. But here's a system of equations. It says, example 4, use an inverse matrix to solve a linear system. Now get if 2x plus 3y equals negative 11, and 5x plus y equals 19. Let's see if this will slide for me. So first thing is how I write it. So I take my A matrix is all the coefficients in front of x and y, negative 2, 3, 5, and 1. The B is the variable matrix. We're solving for what? X and y, x comma y, equal to the numbers to the right, which were negative 11 and 19. We write them down just like x and y. Now, we take this matrix on the left. We want x, y by itself, so let's take the inverse of the one on the left here. All right. Let's make sure this is okay here. All right, sorry about that. Okay. I had a weird graphic going on. So a to the negative 1, or the inverse of a, I take this, I do 1 over negative 2 minus 15, and I change my matrix. Now, I know this is not the greatest problem in the world, but the fraction or the scalar is 1 over negative 17. We have to multiply all 4 pieces by that, and we get this here. From there, you'll see that in front to the left, I put my inverse matrix, and to the left of this matrix, I put it. Remember, the note said to the left, or it won't actually work. If you do it to the right, you're not going to get the same answer. I know if I multiply these together, I should just get my identity matrix with 1s and 0s, and here I'll actually get an answer. Here's what I get, 1, 0, 0, 1 with the x, y. Now, just so you know how we multiply, I mean, I do get 4, negative 1, which is probably surprising that it's simplified so nice. But I do this row times the single column. So I get, what, 11/17, and then we multiply these together, plus these two, which will give me 4 in the end. And then I do this one times these two. Once again, calculator is going to come in handy. You get negative 1. Now, what you should get in the end, it's 4, negative 1. This is how we actually read it. 4, comma, negative 1. So here's an example of how we could use matrices to solve a linear system algebraically. All right, that's it for today. And actually the last lesson. Oh, no, hold on one sec. Let's close that. Sorry about that. So homework. Problem of the day, and then 2, complete the following problems on assignment 5, 1, 7, and 11.